The first problem we solve with FORM, we have named it example B1. It's a problem we have actually already solved before earlier in this week. This involves that cable under tension, and now there are two random variables. One is the yield strength, the other is the axial load. We have solved this, but just let's take a few seconds to recap, and then we will solve this problem with FORM. So it's a known problem, but now we'll use a different method to solve it. There's a new question here, is what are the design values of y and q, and we'll come to that at the end of that solution. So we have to choose a safety margin, and the form that we choose is quite intuitively that it's capacity minus demand. So it's A times y minus q. A is non-random at this point, and we actually have to find the value of A. The transformation we choose, again, we choose the simplest one, the Hasse-Lindh transformation, the second moment transformation. So all we do is u is x minus mu over sigma. So there are two x's, so we have two u's, and it's a two-dimensional problem. So you can actually plot it if we want on a paper. So this gives us, after employing this transformation, that the h, the new limit state function, is a linear function in u1 and u2. A sigma y, sigma q, mu y, mu q, these are all non-random constants. So we basically have to find the minimum distance to the straight line from the origin. And now let's just recap some of the lessons from coordinate geometry long back. So if we have a straight line, ax plus by plus c equals 0 in two variables x and y, then we can look up, or we should be able to remember, that the distance of the straight line from the origin is c over square root of a square plus b square. So that is something I'm sure all of us did a long time back. And then the point, which is something else we also need, the point on this line closest to the origin is x star and y star, and you can either give them in terms of a, b, and c, or a, d, and c, or b, d, and c respectively. So we have to remember these results, and we have to now go back to this line h equals 0 and find out both the minimum distance and the coordinates of the points. So d is c by root of a square plus b square, and x star is negative ad square by c, and y star is negative bd square by c. So with these formulas in mind, now let's put these back on the problem at hand. And so the minimum distance from the origin, beta, is given in terms of the constants of the problem, the cross-sectional area, the means of the random variables, and the variances of the random variables. It's also required that beta is equal to 3. So if you solve it, the answer comes to A as 50 square inch. Now with that answer, we can plug it back and get u1 star, the coordinate of the minimum distance point, is negative 2.8, and the coordinate of u2 star is plus 1. Now this itself is actually very helpful. It tells us that the most likely value, the point with the highest probability on the limit state line, is almost 3 standard deviations below the mean for the strength variable, which is U1, because U1 is a map from the yield strength, and U2 is a map of the load. The most likely value of the load is 1 standard deviation above the mean. So this is actually a very useful byproduct, if I may use the word, of FORM. Not only does it give you the reliability index, but it tells you which point is most likely to happen near about failure. So that we can use it in kind of a design sense, which I'm going to discuss just in a few seconds. So this is the design point. How do we do that? We bring back x1 star from u1 star and x2 star from u2 star. So the most likely value of y, the yield strength, is roughly 22 ksi, the mean being 38 ksi, and the most likely value of the load is about 1100 kilopounds, the mean being 1000 kilopounds. So this is actually quite useful information, because this point y star and q star, they are on the limit state line in the basic variable space. So now here is the idea about how to use this design point or checking point in design is that we can now say that being safe is g greater than 0. So if we can say that ay star would be greater than q star and present the designer this equation to a designer to ensure, then automatically this gives me a value of 50 square inch for the cross sectional area. All I have to do is that tell the designer that these are the design point values. So this way, without even doing reliability analysis or knowing the steps, this design equation would ensure that a beta of 3.0 is observed. So this is an indirect way of achieving a reliability index in design, when the designer does not necessarily need to know the background reliability analysis process, but a design equation, if formulated properly, can ensure that. So that's, and then later on we'll see that we don't have to present these design values per se, but we can present them in terms of nominal values, which the designer is more comfortable with, and present some factors to multiply these nominal values to get y star and q star to satisfy the purposes of reliability.